Good morning, everyone. My name is Celine Turfloth. I am the Aquaponics and Sustainability teacher at CSD.
I'm Molly Denning, and I'm the Sustainability Technician at CSD, and this is the Aquaponics team.
I'm Jack Nixon.
I'm Bella Phil.
I'm Oliver Moss.
I'm Tyler Murphy. I'm Mike Tadra.
And we are the Aquaponics research team. Today we'll be talking to you about the use of black soldier fly-based feed in a recirculating aquaculture system to feed juvenile red Nile tilapia. Today, over 1 billion people are food insecure, and this number is increasing at an unprecedented rate. It is clear that conventional agricultural methods have devastating effects on the environment. As shown in the pie chart on screen right now, agriculture holds one of the largest shares in greenhouse gas emissions out of any economic sector. And with these environmental effects in mind, it is clear that conventional agriculture cannot support current population growth for much longer. This map shows present-day food insecurity and climate change vulnerability, the darker colors highlighting the more at-risk areas. This next map shows food insecurity and climate change vulnerability in 2050, and the best possible case scenario of the two. While this final map shows food insecurity and climate change vulnerability in 2050 and the worst case scenario. And though both of these figures look quite similar, they show the realities that we are facing, but more importantly, that there is still hope in the fight to reduce global food insecurity. But in order to reach these goals, we must explore alternative methods of food production. And aquaculture has emerged as a sustainable alternative to reach these goals. Though aquaculture faces one critical issue, and that's that a vast majority of all aquaculture systems depend on fish meal, which is derived from pelagic fish. Pelagic fish populations cannot support the demand for fish meal for much longer. In fact, 36% of all global fisheries catch are ground into fish meal or made into fish oil. As a result of this supply and demand conundrum, soon the most widely used aquafeed will be far too expensive for use in any aquaculture system, on the commercial or local level.
So this relates to us because we currently use fish meal-based feed in our aquaponics system. And aquaponics is the combination of aquaculture and hydroponics, where we used the fish waste to fertilize the plants in the hydroponic system. So previously, all investigated alternatives that proved successful were blood meal and meat and bone meal, and this was because of their similar amino acid profiles to that of fish meal. But more recently, insect-based feed has become more and more popular, especially after the EU released a regulation in July of 2017 that made it legal to put insect-based meal into fish and poultry feed. So why BSFL? We're using black soldier fly larvae in our study as the protein source in the feed because it is very high in protein, it's cost effective, and it has a very short life cycle of 28 days, and that's the part of the life cycle we're interested in harvesting. It's easily harvestable. So our study is focusing on answering the question, will a BSFL-based meal have an effect on growth? And so our trial is an improvement to last semester's because we're using more subjects per tank, so that's 10 fish per tank, 3 different replicates per treatment, and a longer trial period. This is a photo of our trial system.
Okay, so for our experimental design, we constructed our very own recirculating aquaculture system. This is something that a aquaponics research team has never done at the Highland School before. And so basically what we did is we made 3 tank stands, and we put 3 tanks on each stand, making 9 tanks in total. We put 10 fish in each tank and connected our tanks to our biofilter and our pump. This is the pump and this is the biofilter using PVC pipes. So for our fish feed formula, we followed the Food and Agriculture Organization homemade feed recipe. We took our BSFL and we dried them out in the sun. Afterwards, we put them in an oven and heated them at 170 degrees Fahrenheit. Then we put them in a blender and grinded them into a powder, which we then added our other components of our meal. Our other components were guinea cornmeal, soybean meal, and soybean oil, wheat flour, and a vitamin and mineral premix. We then put water into our substance to make it a dough and extrude it through a meat grinder into strings, which we then cut it up into pellets and dried out in the sun. This table shows our 3 treatments. We have a 0% BSFL protein, 50%, and 100% with a corresponding decrease in fish meal protein. The 0%, which was our control, is the regular fish feed that we use in the rest of our aquaponics system and is what we import from the United States. This is a picture of Bella grinding up the BSFL.
So we measured the fish twice, once at the beginning and once at the end of our 5-week trial period. And we measured the water quality parameters daily. So to measure the water quality parameters, we tested for the dissolved oxygen levels, the pH, the ammonia levels, the nitrite levels, and the nitrate levels. And then we also conducted an ANOVA test at the end of our measurements to see if the difference in means was statistically significant or not. This graph represents the average weight gain in the fish, this axis being the weight and this axis being our treatments and replicates. And then this graph represents the average length gain in the fish. This axis is the length and this axis is the treatments and replicates. So as you can tell in both cases, both graphs, the fish grew more in our control treatment, and with increasing BSFL incorporation, they seemed to grow less. Also, after conducting our ANOVA test, we concluded that the difference in means was statistically significant because the p-value was less than 0.05. This last graph represents the mortality rate in each treatment. This is the number of mortalities, and this is the treatment. As you can see, the mortalities were pretty consistent across the board, and we also concluded that the water quality parameters did not change over our trial period.
We saw that when the BSFL increased in our feed, that the growth rate decreased. As Tyler just said, this was reflected in our ANOVA test that we did because the p-value was less than 0.05. This could have been because even though we fulfilled the protein requirements of a tilapia, we might have not fulfilled the amino acid profile. This is because the tilapia require a higher lysine and arginine levels. Successful studies showed that successful studies used the feed formulation software to get the exact number of nutrients required for the fish to grow. Studies also show that chitin is digested differently amongst the tilapia that we use, so this could have led to mixed results. And chitin is found in the exoskeletons of the insects, so since we have BSFL in our feed, there's chitin in our feed. Also, the mortality rate throughout all the feeds were equal, so this shows that our feed is still viable because even though they're growing at a slower rate, they're still growing, and it did not affect their mortality.
So, our results allude to future potential projects that the Island School could undertake. One of these projects is examining our feed trial's 3 diets over a tilapia fish's lifespan. While our project only aimed at looking at the fish growth worth of 5 weeks of a tilapia fish's life, we could receive potentially different results if we were to see how fish growth was affected with BSFL diets over the course of their lifespan. Since we saw the effects that BSFL has on fish growth, we could also see the effects that it has on plant growth. Another project we could undertake is using all-eluthrin ingredients to formulate a fish feed. We could use ingredients such as moringa, guinea corn, grasses, and BSFL. With the results, we can also assess the viability of the Island School being able to produce its own food. While it is a labor-intensive process, it is a complete possibility. One of the obstacles we would have to overcome is finding the right resources, such as a mechanical meat grinder to grind all of our own feed. Although we did not receive the results that we hoped for, going forward, some of the benefits of a BSFL diet fish feed are sustainability. By making our own homemade fish feed, we would be lessening our reliance on the fish meal industry. We would be minimizing the cost of imported fish meal, as well as minimizing our carbon footprint. A homemade fish feed is also a means of using our food waste, as this food waste would go towards protein for our fish. Our results also showed that BSFL diets had no fatal effect on our fish. For the island school, the focus of the aquaponics system is to have a sustainable means of food production. With this in mind, there's no question that a homemade fish feed holds true to the island school's vision of living well in a place. At this point, we would like to acknowledge the following people: Celine Terfloff and Molly Dunning, Donovan Hepburn, Mike Cortina and Walter Neely for helping us build our system, Maddie Mazzola for taking excellent pictures of us, Austin Stankus for listening to our presentation, the Island School and the Center of Sustainable Development for making this happen, and the Cape Eleuthera Institute for letting us use their facilities. These are our citations. At this point, we would like to welcome any questions. Yes?
So you were measuring the size of the fish, but for aquaponics, I guess maybe it's not a bad idea to have a lot of smaller fish in the same space. I mean, is that necessarily success or not?
So the question is it good to have a lot of smaller fish in the system?
They live the same amount.
Yeah.
Because they're producing your fertilizer, right? So unless a couple big fish in one, but you have a lot of smaller fish.
Yeah, so we used a lot of smaller fish to first, so they're smaller so we can see their growth rate, so they're not too big for our systems. And also, if we used bigger fish, they wouldn't fit, and the smaller fish would just help, I guess, I don't know.
So it's not a bad thing that they didn't grow as big, yes.
No, because they will continue to keep growing, but they're just growing at a slower rate, the ones we used for our specific feed. So they're growing, but it just takes a longer time for them to grow.
Where do you get the insects? And if it did work, so it work a little bit, could you scale it up to feed all of your fish?
So the question is, where did we get our insects, and if it worked, could we scale it up to feed all of our fish? We got our insects from a biopod right in the wet lab, the aquaponics wet lab. We bring the biopod bucket from the dining hall, and it feeds them, and then they grow in there. And when they grow up, they most likely will come back because it's the food source and reproduce more. And then hopefully, yeah, we can, if this proves successful over a longer trial period, we're gonna try to use it in our bigger system to reduce our carbon footprint. Yeah.
Did you find that the size or length didn't increase, but how about the weight of the fish? Would that impact anything? Or, they may have to long
So the question is, did we check the weight of the fish as well as length? So we also checked the weight of the fish, and they did grow. As we said, the control treatment did have more of an effect on their weight and their length, but they're still growing at a reasonable pace for both feeds.
A quick question. The fish meal that you got from the United States as a study, did it have a growth hormone in it?
You asked if the fish meal that we bought from America had a growth hormone in it. It did not have a growth hormone in it, no.
Why tilapia? Can that be other fish, or what's the reason we choose tilapia?
The question you asked is, why tilapia?
I think we use tilapia because they're just an easy fish to have, and they reproduce quickly and they grow quickly, and it's just a good fish to have in your aquaponic system. Yeah, one more. In the back.
You mentioned that you chose that beetle because it doesn't carry germs or diseases. Is there any way to try to use a bug that could, like a mosquito, which obviously is also a pest, and use a bug like that that is known to carry disease?
The question you asked is, could you use a bug that could possibly carry disease? I think that's a question that maybe could be used for future research projects, but currently no. Why we used it is because we know that it's a safe and viable option, and we do need alternatives soon because of the statistics. So it was easier to use bacterial larvae for the reasons listed previously.